So, good evening, students. In the previous class, we started continuous system eigenvalue problem solution, and we took up very simple case of string for the cable problem, and that the partial differential equation was of the second order, which is relatively simpler as compared to the beam case, in which case we'll be having fourth order partial differential equation. So in the previous class, we could able to solve the eigenvalue problem. We got the frequency equation, and then we were seeing some of the property of the L operator and M operator. So from that point, I will start now. So I will share the screen so that. Okay, so on this slide, I was there in the last class. This is the natural frequency expression, and we saw that overtone behavior of the frequency. This is the eigenfunction which we obtained from the after applying the boundary condition. We got the C2 is equal to 0. So if we put the C2 is equal to 0, we'll get the sine function only. So that is there. So beta has been substituted here, this beta, so this is the eigenfunction which we have not normalized till now. So when we will normalize with respect to mass, the A coefficient will change. This function which defines the shape of the mode shape will remain same. So now we'll see the property of the L operator and M operator. So one of them is the self-adjointness condition of the L operator and M operator. So if we have, let us say, two eigenfunction, one is for the rth mode and another for the sth mode, and the L operator of the yr eigenfunction and the sth if we have, and if we do the integration by part of this, so even we can put the L operator here. So this will become like this when we substitute the L operator minus sign is here. So if we do the integration by part of this, taking yr as first part and this as second part, so this will remain as it is. Then integration of this second part will give us this limit 0 to L plus differentiation of this and the integration of this. So this, and this part, if we'll see for any boundary condition, let us say if we are considering the cantilever case. In cantilever case, let us say at x is equal to 0, we have displacement 0. So when we put x is equal to 0 here, this quantity will be 0. And at free end, which is x is equal to L, this particular quantity will be 0, that is tension in the cable. Or if we take fixed case, then both the ends will be having 0 displacement, then also it will be 0. So for all boundary conditions, simple boundary condition, this is becoming 0. So this you will see that we can able to express like this. So dyr dx and dys dx. Now if we change the order of this eigenfunctions, we take the eigenfunction s first and the L operator y second. And if you do the same integration by part like this, we will get similar expression. Only thing will be having s here and y here, and basically these two quantity will be 0. So that means when we are taking the L operator to S, Ys, and multiplied by the YR beforehand, and if we take the L operator to YR and applying the multiplying this by Ys, if these two quantities is equal according to this integration by part, then this L operator is called self-adjoint operator. As I mentioned in the discrete system, this is similar to the symmetry of the stiffness matrix. So L operator is related with the stiffness. So if this condition is prevailing, we'll call this as a self-adjoint operator. Normalization of the eigenfunction, as I mentioned in the previous slide, generally we do with respect to the mass. So here mass operator we are applying to the eigenfunction, and if we, because in this particular case M operator is just the mass per unit length rho, and I think I should have here similar to this, we should have YR outside, YR similar to this. So if we normalize this, so over here M operator is rho, and we need to do operation of YR, but because this is constant, so YR will be as it is. So this will be square of the YR rho, and we are equating this equal to 1 to normalize the eigenfunction with respect to the M operator. And this we need to normalize for each R. R is equal to 1 to up to infinity, as we used to do for the discrete system. We need to normalize with respect to each of the eigenvector. So here we are normalizing each eigenfunction with respect to equal to 1 with respect to mass operator, M operator. If we do, now we will substitute YR, which we have this expression YR is equal to. So if we substitute this here, integrate it, we'll get the AR expression in terms of the, so AR will get this. So this is the amplitude of the eigenfunction after normalizing with respect to mass. So the eigenfunction, so orthonormal set of modes can be expressed because this has been normalized with respect to mass. So amplitude has been replaced by root 2 rho L. And this function remains same because this is defining the shape of the deformation of the various points onto the string. And this is defining the amplitude part, which we already know for eigenfunction. This is arbitrary, but here we have normalized with respect to mass, so we got this value. Now this eigenfunction can be plotted for various value of R. So this is one of the, so here is representing, X is representing the location of the string. So string was attached at 0 position and L position, and this is the shape of the string corresponding to the first natural frequency. And this is the, if we put R is equal to 1 here, we'll get the shape. So here, because we have been normalized this with respect to mass, so this amplitude part is coming here, the maximum part is root 2 by rho L. So this is the shape corresponding to the first natural frequency. So when the string or the cable is vibrating in this particular form, so frequency of that will be equal to omega 1. So other way around is also true, that if the frequency of the vibration is omega 1, it has to vibrate with this particular shape. So 1-to-1 correlation is there between the natural frequency and the eigenfunction. Coming to the second mode, this is the corresponding natural frequency, twice of that, because we had the R term here. So, and the eigenfunction will be this. So the shape of the mode eigenfunction will be like this. So at fixed end, they are 0, but at one midpoint also there will be displacement 0. Generally, we call this as a node. So there is nothing is fixed here. We have not constrained this particular cable by some external constraint that should be 0 here, but because of the mode shape, this particular point at L by 2 corresponding to the second natural frequency will remain fixed. So in other extreme, it will come this side, and so this remain the same at this particular point, and this is called node, where the displacement in between the support, if is 0 all the time during motion, then is called node, and the maximum displacement location is called antinode. Here also this antinode. In between there is no 0 displacement here, so here there is no node position. 0 and L position is because of the external constraint. So this is here, the node is there. Similarly, if you go for third mode or fourth mode, the number of nodes will be increasing. That I will show in the next slide through a simulation. Now the node position can be obtained by equating this eigenfunction equal to 0 and solving for x. So if we equate this equal to 0, so here we're equating this equal to 0, and if we solve this for x, so because this is sine function is there, so sine function will be 0 at n pi. So if we equate this equal to n pi, x can be solved. So n L by r will be the node location. So when we are talking about so this is the for any number of like if you are talking about n is equal to 1 or n is equal to 2, so corresponding locations we can able to get from here. This is the same thing in the animation part. So first mode, you can see how the string will vibrate, and the frequency of this will be omega 1. This is the second mode in which you can see one node is there that remains fixed onto the string, but other part is having motion. Similarly, in the third mode, we'll be having two such nodes, and in between it will be having displacements. Similarly, in the fourth mode, we'll be having three nodes. So this is the animation of the string which is fixed at both ends, and during various excitation or to do free vibration at different modes, how they will vibrate. Now I'll take up another case in which we are talking about the longitudinal vibration of a rod. So at very beginning, we derive the equation of motion for such axial vibration of the rod for varying geometry. But because now we are solving the differential equation, so taking such complex geometry will be difficult. So we'll be taking a uniform axial rod. So it is vibrating axially. This is a continuous rod. Here, initially, we'll take the case of the cantilever case. In the string case, we took the fixed. Here, we'll be taking initially the cantilever case in which one end is fixed, another is free. For this system, we derive the equation of motion, which was partial differential equation of second order. And because we derive the kinetic energy, potential energy, and using Hamilton principle, when we were in the second chapter, we derived this equation of motion, and we got the associated boundary condition in this form, in which we had this as the axial force, and this is the displacement variation at 0 x is equal to 0 and x is equal to L. So this is the boundary value problem. So this is the governing equation. This is the associated boundary condition which we need to satisfy when we need to solve this equation. For cantilever case, at x is equal to 0, we'll be having displacement 0. This will be 0. Axial force will not be 0. But at free end, because it can have displacement, so this quantity, which is axial force, will be 0. I think this should be directly, we can write this as it's not required. So these are the boundary condition for the cantilever case. This is a general boundary condition which we can take all kind of boundary condition. So now we are trying to solve this particular problem in which one end is fixed and the other is free and the beam is uniform. So that means area is not changing and mass per unit length is also not changing, that is constant. So the same thing which in the previous slide, I think here fixed end, so displacement is 0, and here we have this shear, the axial force 0 at the free end, and we are talking about the axial vibration. It is very important to note that this is the axial vibration, not the transverse vibration or the bending vibration. In bending vibration, we have fourth order differential equation, but in the axial vibration, we have second order differential equation. So now we'll go back to the general formulation, L operator W lambda M W. So L operator here, if you compare this eigenvalue problem for the specific case of the axial rod and general one, we'll see that minus of this except the ux will be the L operator. So L operator is this. M operator is simple M because simple M is there. Lambda, we compare here, lambda is the omega square. Because M is mx, so lambda is omega square. Earlier we related the omega beta in the eigenvalue problem. I think we'll be using this in the subsequent slide. So here the order of differentiation of this L operator is 2. So we'll equate 2p is equal to 2. So that will give us p is equal to 1, because the number of boundary condition at each point will be depending upon the p. Q is equal to 0 because there is no differential order here. So at x is equal to 0, we will be having only one boundary condition because we have p is equal to 1. So at x is equal to 0, u0 is 0. And yeah, this is the boundary condition. And if you compare this with this boundary condition, we can see that the B1, because P, the I can go from 1 to P is 1. So B1 for the x is equal to 0 case will be B1 is equal to 0 because there is no differential operator here. So B1 is equal to 0. Here, in the second case, x is equal to L. Here also, we'll be having P number of boundary condition, that is 1. This is the boundary condition. And if you compare this with this, we'll see that the operator B1 will be EA d by dx, because B is a differential operator. In the previous case, there is no differentiation, so B1 is 0. The order of differentiation is 0. It's not key, we need to substitute B1 is 0. This operator onto the W is no differentiation, meaning of that is that. And here we have B1 is equal to EA by dx. So this is the comparison with the general eigenvalue problem, which we define in the L and M operator form. Because we'll be using these L operator and M operator again and again, especially when we go for the solution of this differential equation using the approximate method. So that's why here always we are comparing with the general operator and the specific operator. Now, now we are considering the uniform rod. So that means EA is constant. So that has come out from the differentiation. So, and also M is now constant. So eigenvalue problem we wrote like this with EA constant and M as constant. And now I divided by EA. So I got this where beta square now I'm defining as omega square M by EA. So once I divided by EA, so this quantity which is I'm defining as beta square. Beta square so that the functions which we'll be getting in the solution of this will be having a simpler form. Otherwise, it will come as a square root of the beta. So for this second order ordinary differential equation, the solution, because the second order two constants will be there and the solution will be of this form, C1 sine beta x plus C2 cos beta x. If you remember for the string problem also similar solution was there. Only thing is beta was different, defined differently, but this is identical to the previous one. In fact, if you compare this equation with the previous string problem, they're identical. Only thing is the variables are different. Here it was y, here it was beta defined differently in terms of tension and the other quantity, but here now it's defined like this. So this is the our solution we are assuming, and C1 and C2 we need from the boundary condition of the problem. So this is the boundary condition which involves the derivative also of this function. So we have taken the derivative of this. So C1 beta cos beta x minus this. So now we will apply the boundary condition. So first this one. So u is equal to 0 is 0 because fixed and displacement is 0. So if you put x is equal to 0 here, so first term will be 0. So that means it will give us C2 is equal to 0 because cos 0 is 1. So we got C2 is equal to 0. So this quantity is 0. Now in the second boundary condition, because this is homogeneous boundary condition, EA is having no meaning because anyway this cannot be 0. So we are satisfying this part only. So u du d at L, derivative of u with respect to x at L is equal to 0. So derivative of this, so we are C2 is 0. So we are not taking this, only C1 beta. So where x is there, we are putting the L. So we got this expression. Now C1 cannot be 0 because if C1 is 0, then both C1 and C2 is 0, there is no motion. Only beta also cannot be 0. If beta is 0, then the natural frequency will be 0. But this is fixed support is there, so that is not possible. So only possibility is this last term cos beta is equal to 0. So this is the frequency equation for the axial rod case with the uniform cross section and the uniform mass distribution. And beta we are defined like this. So now we'll solve this frequency equation, which is will be having infinite solutions. So here beta r is equal to this will satisfy the this. So you can see that all the odd numbers when it is coming here, then it is satisfying here. So pi by 2, 3 pi by 2, those solutions will be satisfied here. So this is the solution of the beta. So now beta is related with the natural frequency. So how it is related in the previous case we have seen this one. So now natural frequency can be written in terms of beta, and beta can be subtracted from here. So this is the solution we have subtracted. So this is the natural frequency of the system where R will be 1, 2, 3 like this up to infinity. Here now you'll see that the natural frequency of the axial rod depends upon Young's modulus, the area of cross section, mass per unit length, and length of the rod. Earlier in the case of string problem, it was depending upon the mass per unit length and the length, and also the tension in the string. So for various value of R, like this is the first natural frequency, if we put R is equal to 1, this second natural frequency, third natural frequency. So here we are getting natural frequency. So earlier, what was the case? We were getting the second natural frequency as the twice of the first one. But here now we are getting 3 times the first one. Earlier we got the third natural frequency 3 times the first one, but here now we are getting the 5 times. So the previous trend is not here, but there is still some integer multiple relations are there, but some of the intermediate factors are missing here, and we can go on writing omega 4 omega 5 here. Now the normalization of the eigenfunction. So eigenfunction is what here? You can go back to the previous slide. So here we got the C2 is equal to 0. So once C2 is 0, so Ux is equal to C1 sine beta is the eigenfunction. C1 is constant, which can be normalized with respect to mass to get the C1 value, as we got in the case of the string problem. So this is the AR I'm writing. Instead of C1, I'm writing AR, and I'm defining. I'll replace the beta with the R this term. So this is the eigenfunction for rth mode. Now I'm normalizing this with respect to the M operator, which is not differential operator. So I'll get the AR this like this. So this is similar to the previous expression. So this is the normalized or orthonormal eigenfunction where R is 1, 2, 3. So for different mode, this shape will remain fixed. Amplitude is arbitrary anyway in the eigenfunction. And here also, if we want to find out the node position, we need to equate this equal to 0 and solve for x. So because this is a sine function, so every n pi terms will be giving us the 0 value. And if we solve for x from here, so these are the node positions which will be giving us in the axial rod case, and how the vibration will take place. Now we'll see in the slide. So here we have the cantilever beam case we have considered. This is the first mode, natural frequency. And the shape of the vibrations will be like this. Here to visualize this displacement, you see that this particular rod is vibrating axially. This end is fixed. So displacement will be 0 at corresponding to that. But as we'll go along, every point will be having motion in the x direction, to and fro motion. So at free end, we can expect that the displacement will be cumulative and the maximum displacement will be there at the here. So maximum displacement will be here. So at intermediate point, these are the displacement. So I have shown in the vertical direction the axial displacement. Okay, these are not the transfer displacement, axial displacement. So every point on this particular body is moving to and fro. And in the first mode, we will be having maximum displacement at free end and 0 here, because the boundary condition is like that. For the second mode, because the boundary condition is still this end should be the displacement 0, so that is coming here. but according to the previous formula, we'll get the one node position here. And for this, I think this will be 2 by 3L position. So here, there will not be any displacement. So if you want to visualize this, in this particular beam, when it is vibrating with the second mode, at one point here, which will be 2L, 2 by 3L position, there's no displacement. And as you are going this side or that side, the displacement will increase here also. And because again here displacement is 0, so displacement will be 0. So here you can see the displacement is increasing, maximum here. Then because there is a node here, there is no axial displacement at that point. And then again, the displacement is increasing. And same thing for the third mode. Here we'll be having two node positions. That positions also we can able to get from the previous expression. And here either side will be having displacement. But here one interesting thing we can see even here, if we take two points either side of this node, this side and that side. So this side will be having a point, let us say positive displacement, let us say in the x direction, positive x direction. So this point which is identically away from this node will be having negative x direction. So if node position is here, one point which is here maybe is moving in the positive x direction. Another identical position here will be moving in the opposite x direction. So this particular thing is positive displacement, this is negative displacement. So the same beam along the length, because of the mass distribution, will be having different displacement. Even they can have different direction of displacement. So node will decide the direction of the displacement. And here you'll see that the third mode, this part of the beam will be having, let us say, positive x direction, then this will be negative x direction, this will be positive, and they will swap also. When this becomes negative, this will become positive, this will be negative. So the same beam at third mode will be having three parts, not equal parts, but three parts, and every point will be having a different displacement, and maybe in between they can have different direction of the displacement in positive x direction or positive negative direction. So this is the analysis or the visualization of the axial vibration, because axial vibration is more difficult to visualize as compared to the bending vibration. So we are talking about the vibration of the beam which is moving axially. So that was the one case. Another case of the longitudinal vibration rod I will take up, and then maybe at the end I will ask the questions. So here I'm taking another axial rod, and this is having no support. This is freely hanging on the air. So here also this support is free. Here also support is free. It's similar to maybe aircraft is moving on the air, or a particular rod is hanging by some string vertically. That is also another example. So both the boundary conditions are having the same, that there is no axial force at the both ends, but displacements are not zero at the both ends. Now the property, the self-adjointness and the positive definite operator, we can able to check as we did for the cantilever case. Here also they will be same. They will be self-adjoint and the positive definite. So like here for positive definiteness, we can, for self-adjointness it will be same. For positive definiteness, we are checking here. So here we are doing integration by part. When we are substituting the L operator, operation is same as the previous one, but the interpretation will be different. So here when we integrated by part, the first part here also is 0, and we got this. So in the previous case also we got the exactly same expression, but now let us see the interpretation of this. So this quantity, because here UR and UR both are same, so we are checking the positive definiteness. So in that case, both are UR. In the self-adjointness case, we took the R and S, which anyway will be similar to the previous case, because we will get R here, S here, and we can able to check the L operator is self-adjointness. Here we are checking the positive definiteness, in which both eigenfunction we are taking the same. So we got the this as square of this. Now if you see, EA is the constant term. They cannot be zero, area and Young's modulus. This quantity is square. So that means this quantity remain positive. Remain positive. That means this quantity will be zero when UR is zero. That is fine. Okay, so there is no problem. But if UR is constant, that means there is some displacement which is constant displacement. Then what will happen? A constant derivative, if we are taking, that also will be zero. So that means what is happening here? This particular quantity is zero when UR is zero, but it is zero when UR is constant, which is possible in the case of free uh, boundary condition. It's not possible for the cantilever case, because cantilever case cannot have the constant displacement, because one end is fixed. So constant displacement is only thing is zero, because we cannot move the support. Support is having zero displacement. So all the points will be having zero displacement. So uh, the displacement equal to constant is not possible in the cantilever case. But in the free case, it is possible that all the points can have same displacement. So UR, if it is constant, then also it is constant. So that's why it is called positive only. So it is not positive definite, because this quantity can be zero when there is a constant displacement because of the derivative term in the expression. M operator is always positive definite, because we have the kinetic energy is zero when velocity is zero, and it cannot be zero for any other velocity, in which L operator is positive, M operator is positive definite. So if you recall, for the case of matrices in the discrete system, uh, stiffness matrix, when it was uh, positive, and mass matrix positive definite, then we had the case of the semi-definite system. So some analogy is there between the continuous system and this particular discrete system. Now we'll come back to the original problem, this free case. Now we'll apply the boundary condition. The solution, because we have the same differential equation, only thing the boundary condition is changing. So boundary condition contain both slope. So this expression we derive for the case of the cantilever case. So we'll use this. So when we are using one of the boundary condition, this one, then x is equal to 0. So we are getting, when we put x is equal to 0, we are getting the C1 is equal to 0. So C1 is 0. Is when we have x equal to 0, x is equal to L. And then in the remaining part, by removing the C1 part here, if you put this here, so C2 B beta sine beta L, this is equal to 0, because that is also free end. So here if you see C2, if is 0, then no motion. All C1 is 0, then C2 is 0, then there is no motion. Beta cannot be, beta here can be 0, because here we have the rigid body mode and beta L as we had earlier. So here you can see that as compared to the previous case, uh, we have the 0 also here. Earlier we started with the 1, 2, but here beta can also be 0. That means one of the natural frequency can be 0, which we already know that for semi-definite system, one of the natural frequency can be 0. So here one extra natural frequency is 0 is also coming, which will belong to the rigid body mode, having all the particles in the system have same displacement. So this beta L will give us this because for every pi sign will be 0. So this is the solution for so this is the frequency equation. Okay, this is the frequency equation, which because beta is related with the natural frequency. Now, corresponding to the eigenvalue beta is equal to 0, let us analyze this mode eigenfunction. So when beta we are representing as beta naught because r is equal to 0. So beta naught is 0. So eigenfunction we have of this form. This is actually this is for the all other case other than the beta naught is equal to 0. For beta naught is equal to 0, we are deriving the eigenfunction from here. So we are going back to the equation of the eigenvalue problem, and beta we are substituting here. So beta naught is 0, so this quantity is 0. And so this is 0, then we got this. And if we integrate this once, we'll get some constant this side. If we integrate twice this, I'll get another constant. So a naught and a naught prime, two constants will be there corresponding to this beta is equal to 0. This is corresponding to all other natural frequency other than the 0 natural frequency. So let us see this. We apply the boundary condition now. Applying boundary condition again, we did because boundary condition contain the derivative of this. So if we take the derivative of this, we are having, and we are putting x is equal to 0. On the left side, we had this quantity 0 in the boundary condition. This boundary condition, x is equal to 0. So if we do that, so because x is equal to, anyway, once we integrate this, a naught only will be left out like this. So a naught will be 0. So if we apply one of the boundary condition, we are getting a naught is equal to 0. That means this is 0. So once that is 0, then this will be equal to a naught. Even the second natural frequency, second boundary condition will satisfy. That will not give any additional thing. So you can see that the corresponding to the 0 natural frequency, the eigenfunction is a constant quantity. That means the rigid body mode, all the particles, if we take x is equal to any value, will get the same displacement. So this is the rigid body mode, which is there for the unconstrained system, like free case. Now, if we let us say there is a resultant force in the longitudinal direction of this particular beam, Ft is the external force. So according to the Newton's law, the external force is equal to whatever the inertia force. So inertia force is mx, and this is the velocity, the displacement's derivative with respect to time. So this is the acceleration term. And if we substitute the separation of variable expression here, we'll see that the f will take the derivative and it will come out, and this will be the expression because this time dependent term cannot be 0. Here finally, because in the free vibration there is no resultant force, so we are keeping ft is equal to 0. So we got this integral equal to 0 because ft cannot be, the small ft cannot be 0. So this expression I have written again here. So this one is the eigenfunction corresponding to any other flexible mode, and eigenfunction corresponding to the the zero natural frequency is a constant. So this we can think of that there is a constant here multiplied by the eigenfunction at any other mode is equal to 0. So this is representing that the eigenfunction corresponding to the rigid body mode and the flexible mode are orthogonal to each other. So this expression is indicating that even the rigid body eigenfunctions are uh, orthogonal to this eigenfunction related to other flexible mode, which is r is equal to 1, 2, 3, 4. For elastic mode, we have already this kind of expression in which we normalize the eigenfunction with respect to the mass operator, and when r and s are equal, then this is equal to 1, otherwise this is 0. So here even this has been included here. When r is equal to 0 and let us say s is equal to 1, so this will be 0, this will be 1. Because this is a constant, this will come out having no meaning. So we'll get the similar expression like this. So this particular the normalization and the orthogonality conditions have been combined here, even for the rigid body mode, r is equal to 0. That is very important. So rigid body modes are also orthogonal to their higher modes. Now coming to the eigenfunction corresponding to the flexible mode, this is the expression. This has not been normalized. Here we can able to normalize by substituting here. But here if you want the node position again, so we need to put this quantity displacement equal to 0 and solve for x. So if we solve for x, we'll get this equal to 0. So cost function is 0 for all the odd value of pi by 2. So if we equate this quantity equal to 0 and solve for x, we'll get expression for this, which will give us the node position in the flexible mode. And this is the mode eigenfunction, how it will look like for rigid body mode. All the particle in the beam will be having same displacement. So this rod will be moving, all the particle will be moving in the same displacement. So that's why it is shown as a constant value. And corresponding natural frequency will be 0. So that is corresponding to rigid body mode. So this was not there in the previous cases, in the positive definite cases. This particular mode is there only for the case of semi-definite system in which one of the natural frequency is 0. Then for first natural frequency, now you can see because this is free end, so both the ends are having displacement, they are not 0. For cantilever case, we had one end 0 and other was free, but here we have both the ends are free, so they will be having displacements, and in fact there will be one node in between. So the left part of this beam will be vibrating, let us say in the x positive direction, then the right part will be moving in the negative x direction. So they will be having opposite motion all the time. When this will be having negative x direction, this will be having positive x direction. So in between there is a node, there is no displacement. I'm talking about the axial vibration. So as you go along this beam, this side will be having more and more displacement. Similarly, other side also will be having more and more displacement, but both will be having opposite motion. So if we take from midpoint identical two positions, this will be moving, if it is moving in the negative x direction, this will be moving in the positive x direction. And then they will swap their positions. In the second natural frequency of the flexible mode, there will be two node positions which can be obtained from this expression. So here, this part, so there will be three parts of the beam. Will be having a node in between. So this part will be having, and this part will be having same direction of displacement. This part in between will be having opposite to the this two. So very interesting behavior we will see in the third case, in which this two part will be having same displacement directions, and this will be having opposite, and every point is having different displacement. Even the direction is changing. So this is the longitudinal vibration of rod for free case, which was semi-definite system. And so I will stop here. I'll take up the questions you have on the, because these are the basic theories. So they have been solved long ago, and then they're part of the example. So in fact, these are the examples only, but as I mentioned, in the continuous system, very few cases we can able to solve the closed form solutions. So like cantilever case or free case or fixed case, that kind of simple boundary condition we can able to solve in the closed form, in which we can get the frequency equations explicitly. But for other boundary conditions and complex shape of the beam or the rod, will be having difficulty using the procedure which I'm explaining, and then we need to go for the approximate solution for such cases. So if you have any questions on the today's presentation, you can ask me. Okay, so yeah, Sai Guru.
Sir, any example for this free case, sir, for longitudinal vibration of rods?
As I mentioned, one of them is the aeroplane which is moving on air. So the whole aeroplane can be taken as a axial rod, as a very idealistic way. Okay, so aeroplane is not hanging anywhere, is moving in air. Another case can be a long rod that is hanging through some string. Okay, so as such in the so that could, so this very best one is the aeroplane one, in which the things are, or maybe you can think of a ship which is moving on a sea. Okay, so as such, nothing is constrained there. It can move along the surface of the sea. So these are the, so whole ship can be considered as a longitudinal vibrations. There because waves are also in that direction. They're forcing the sea in the axial direction only. Okay, so these are the some of the example we can think of.
Okay, sir. Thank you.
Yeah. Any other question? Okay. So we'll continue this kind of formulation for now. We'll take up another case in which we'll be having the boundary conditions will contain the eigenvalue. That will be more complex to handle. So till now our boundary conditions were simple. So now in the next class we'll take up case in which the eigenvalue is there in the, not only in the eigenvalue problem but also in the boundary condition. So that is, even the orthogonality conditions will, the expressions will change, and the property of the self-adjointness. So that becomes more complex. So, but just to have feel of the complexity involved in the closed form solution, we'll pick up that, and maybe I think after 2-3 lectures, we'll go for the approximate method. So with this, I will now close. So Have a nice evening. Goodbye.